Okay, so now we're going to look at geometric sequences. So geometric sequences, remember a sequence is just a function that takes on the natural or counting numbers as its domain. So if you restrict any function's domain to the set of counting numbers, 1, 2, 3, 4, and so forth, you get a sequence. And once again, we're going to change the notation. We're going to change the notation from, well, our function, we're going to call it a. And instead of an independent variable x, we're going to use the independent variable n. And instead of using the old function notation a of n, we're going to use this notation where the independent variable becomes a subscript. All right? And the kind of functions we dealt with before were linear functions. Those created arithmetic sequences. Now, we're going to deal with exponential functions of the form c a to the x. That a is the base of the exponential function. Well, actually, let's use b so as not to confuse it with this over here. B is the base. Usually when they introduce it, they use a in college algebra books. A lot of them I've seen. Okay, so the characteristic here is that the exponent, the independent variable, are one and the same. The exponent here is the independent variable. So this is not a linear function. It's an exponential function. And we're going to look at it in terms of sequence. So it's going to be c. And instead of b, the base, I'm going to call the base r. And the reason I'm calling it r is going to have a name. It's going to be called the common ratio. It's actually the ratio between consecutive terms of the sequence. Just like in the arithmetic sequence, there was a common difference between consecutive terms. In the terms of an arithmetic or a geometric sequence, there is going to be a common ratio between consecutive terms. And the independent variable here was x. The independent variable here is n, and that is the exponent. So we're going to be looking at sequences of this form. So let's take a look. The first term of this kind of sequence would be just c times r to the first power. So it's just cr. The second term would be equal to c times r squared, which is cr times r, but remember cr was a1. So this is really equal to a1r. a1r to the first power. a3 is equal to c times r to the third, or cr times r squared. Remember, cr is just a1. That's multiplied by r squared. So we're getting an expression here in terms of a1, the first term. All right? So if you continue, you see that a4 is equal to c times r to the fourth, which turns out to just be a1r to the third. And if you continue with this pattern, you get that an, the nth term, is going to be equal to a1, well, it's going to be c times r to the n, which is just going to turn out to be c times r to the first times r to the n minus 1, or a1 times r to the n minus 1, if you continue with the pattern. So this is an expression for the nth term. All right? So when you're dealing with a geometric sequence, the formula for the nth term is an equals a1 multiplied by r to the n minus 1 power. That's the nth term formula for a geometric sequence. So for example, we have questions where we give you find the nth term, and let's say we want to find a I don't know, 4. Oops, not superscript, subscript. Okay, and a1 would be given to us as, let's say, 24, and r as 1/2. So the parts here, a1 is the first term. It's what you get when you plug 1 into the function. R is the common ratio. It's the ratio that's shared by consecutive terms, any pair of consecutive terms. All right, so let's see. Judging by this nth term formula, I see that an is equal to a1, which is 24, times r, which is 1/2, to the n minus 1 power, n minus 1 power. All right, I'm going to simplify that. That's going to equal 24 times 1/2 to the nth power times 1/2 to the negative 1 power. Because when you multiply these two together, you would add their exponent, giving you this expression. When you multiply two things with the same base, you add the exponents together, you get exactly this. 1 over 2 to the negative 1 power is just 2. And then 2 times 24 gives me 48. So the nth term formula is 48 times 1/2 to the nth power. That's the nth term formula. All right? The next thing they want us to find is the fourth term. So A4, the fourth term, is going to equal 48 times 1 over 2 to the fourth power, which yields for me this. It's going to be 48, and then that's 1 over 16, 1/2 to the fourth power. So I get this is 48 times 1/16, which is 3. So the fourth term is the number 3. All right, so that's one use of the nth term formula. That's when you're given a1 and r explicitly. You can come up with the nth term, and you can find any specific term. All right, let's see. Now let's say you're given something like this instead. And let's say we're going to find a 8. And let's say we're given this. Instead of being given a1 and r, let's say we're given this, the sequence itself. 243, 81, 27, 9, 3, and so forth. So it continues on in that fashion. What you want to do is you want to find the common ratio if you know that the sequence is geometric. Well, actually, finding a common ratio proves that the sequence is geometric. Let's see, 243 over and 81, if you take the ratio of those consecutive terms, 81 and 243, you get 1/3. All right, let's see. Then we're going to take these two. That's going to be 27 over 81, which is also 1/3. Those are equal. Then we're going to get 9 over 27, which is also 1/3. Those are equal. And then we're going to get 3 over 9. 3 over 9 is also 1/3. Every single one of these is equal to 1/3. That's the common ratio. And we also have the first term, a1, is equal to 243. So I can find the nth term. The nth term then is equal to a1, 243, multiplied by the common ratio, which is 1/3, raised to the power of n minus 1. Raised to the power of n minus 1. And there's the nth term. You can simplify it. 243 times 1/3 to the nth power times 1/3 to the negative 1 power. And 1/3 to the negative 1 power is actually 3. All right, and when you multiply 3 by 243, you get, let's see, that's going to be 9, 12, 6 and 7, 729 times 1/3 to the nth power. So I have my formula for an. I know that an is equal to 729 times 1/3 to the nth power, and they want me to find the 8th term. So a8 is equal to 729 times 1/3 to the 8th power. Well, that's 729. And let's see. 1/3 to the 8th power. This is first, second, third, fourth, fifth, 6th, 7th, 8th. So let's calculate that as 6,561. So we get 729 over 6,561. Which reduces 729 over 6,561 to 1/9. 1/9. So I have the AN is equal to 729 times 1/3 to the nth power, and I also have that A8, the 8th term, is 1/9. 1/9. So there you have it. That's the nth term. If you're given the sequence itself, that's how you do it. And I want to draw your attention back to one thing here. What if you're not given A1? There are some examples where you're not given the first term. So what if you're given two arbitrary terms, AI and AJ, let's say. So we have two arbitrary terms, neither one necessarily being the first term, and I want to stipulate that I is a bigger number than J, okay? So what we're going to do here is we're going to try to find out what the common ratio is. We're going to try to see if we can use the formula to find the common ratio. Well, the common ratio is the ratio between consecutive terms, and let's see. Let's just find the ratio between these given terms. I is bigger than J, so I'm going to take AI and divide it by AJ, because this one is later in the sequence. Alright? That's going to equal, let's see, it's going to be A1 times R to the I minus 1 divided by A1 times R to the J minus 1. The A1s cancel each other out, and this actually turns into be R to the I minus 1 minus J minus 1, which simplifies to just R to the I minus J. So it turns out I can use this to find R. I know that I over AJ is just going to be equal to R to the I minus J. R to the I minus J. So I can take the I minus Jth root here and finish this problem off. Alright, let's take a look at an example where we're going to use this, where they don't give us the first term, but they give us two subsequent terms. Let's say we know that let's see, 3 is equal to 32, and that A6 is equal to 256. And we want to find AN. Let's say this is the example we're looking at. We're trying to find AN, the nth term. And we know A3 and A6. So we can't use this formula, AN necessarily equals A1 R to the N minus 1. We can't use that because we don't know A1. And we really don't know R. But here we have something that can help us to find R. This says that if I take AI, remember here that I was larger than J. So if I take A6, 256, and I divide it by AJ, AJ is 32, then it'll equal R to the I minus J, which is 6 minus 3. That's what this formula says. We can use this now to find R. Let me get rid of the formula, but you see where everything comes from. AI, AJ, the two things that are given. I is 6, J is 3, R to the 6 minus 3, this formula. Alright, so this says, let's see, we have 256 divided by 32, which is 8, is equal to r to the 6 minus 3, which is 3. So if you take the cube root of both sides, you see that r is equal to 2. So we have the value of r. Now that we have the value of r, we can find the value of, well, we don't need to find the value of a1. We can actually just find whatever that constant is, remembering that an is actually equal to some constant times the common ratio to the nth power. If you don't write it in terms of a1, that is. If you just write it in terms of a constant. So we have a lot of information. We have r, and we have a value of n and an for that value. So let's use this. We know that a3 is equal to some constant times r, which we just found as 2, to the third power, a3, right? That's equal to the number 32. So I get that 2 to the third power is 8, c is equal to 32, in which case we see that c is equal to 3. So I now know c is equal to 3, so my nth term, the nth term is equal to, let's see, it's going to be c, which is 3, times r, which is 2, times r, which is 2, to the nth power, And there's the formula for your nth term.